Now the next thing we look at is basically the relationship between voltage and electric field. Okay. So we know that basically charges move under the influence of electric fields. So we need both charges and electric fields for some interesting things to happen in electrical circuits. The way we provide the fields are by providing voltage differences between different points. Okay. Now what is an electric field? Electric field basically is something which accelerates a charge. That is, if you place a positive charge in an electrical field, that positive charge will be accelerated in the direction of the electric field. Okay. Now the obvious analogy for this is the gravitational field. If you place a mass in a gravitational field, it will be accelerated in the direction of the gravitational field. Okay. So let me put down this analogy here. So you can think of this as Earth's surface, but of course it could be anything else which creates a gravitational field, and I will consider a field, gravitational field, to be pointing downwards. And similarly, let's consider some source of electric field. We won't worry about what it is. I'll just show it in downward direction because I showed the gravitational field in the downward direction. So let's say this is the electric field. Now we know that if we place a mass m in a gravitational field, of course it falls in the direction of the field. The field accelerates it. Okay. So similarly, if you place a charge q in an electric field, it will be accelerated in the direction of the electric field. Okay. Now again, you have already done such kind of calculations. That is, if you place a mass in a gravitational field, it will get accelerated after a certain amount of time. What is the velocity taken on by the object, and so on. So similarly, you can do so for the charges in electric field. But now we are not interested in such details of the motion of the electric charge. Okay. So what we'll do instead is, instead of dealing with fields and accelerations of charges directly, we'll look at potential energy or potential of the charge. Okay. What does this mean? So let's say an object, again I'll use the gravitational analogy first. Let's say it's at some height h1 and it falls to another height h2. Okay. So it falls from here to here. You know that the object will gain energy. Okay. So perhaps initially it was being held stationary, and then at this point, when it goes from here to there in gravitational field, it will gain some energy. And you also know that the amount of energy gained is mg h1 minus h2. Okay. Okay. Then we also know that the voltage is related to the integral of the electric field. Okay. Such that when the charge moves from point 1 to point 2, okay, it gains an energy which is equal to q times V1 minus V2, where V1 is the potential at point 1 and V2 is the potential at point 2. Okay. So you can see the analogy between energy gained by an object falling in a gravitational field and the energy gained by a charge which is falling in an electric field. When I say falling, I mean being accelerated by the electric field. Okay. So now, instead of dealing with the gravitational field directly, what can be done is to deal with the gravitational potentials. Now you know that the energy gained is proportional to the mass itself, and mass is the property of the object that is placed in the field. Okay. Whereas this part of it, g times h1 minus h2, that's a property of the field itself. So that is termed to be this g times h1 minus h2. This is basically the potential difference between 1 and 2. Okay. So in this case, it's the gravitational potential difference. Similarly, this V1 minus V2 is also the potential difference between 1 and 2. This is the gravitational potential difference, and this is the electrical potential difference. Okay. Now, from this, it should also be clear that what matters is the difference in potential between 2 points. Okay. So that's why it's many times called the potential difference. Voltage is called the potential difference because what matters is the difference in potentials. Because we chose, let's say, the Earth's surface to measure these heights h1 and h2, but we don't have to do that. We could measure it from the bottom of a pit or from the top of a building, where then h1 and h2 will be different from before, but h1 minus h2 will be exactly the same as before. Similarly here, what matters is the difference in potentials between 1 and 2. Okay. The potential at 1 or 2 can be arbitrarily assigned to any value. That is, they can both be arbitrarily shifted by a certain value by shifting the reference. Okay. But the difference between them will remain constant. So basically, instead of using electric field, which accelerates charges, we will use potential difference between 2 points, which also accelerates charges. Then we will not characterize it as acceleration of the charges, but as the rise in potential energy. But also it's not the energy itself, but we normalize it to a unit charge so that we get rid of the charge itself, which is the property of the object, and keep only the potential difference, which is a property of the field that the charge is in. So the potential energy gained by falling in an electric field is nothing but the charge times the potential difference between the 2 points. Okay. So what is the bottom line here? Instead of dealing with charges and electric fields, we deal with currents and voltages. You can see that these are some sort of aggregated quantities. Okay. Current is basically the total amount of charge that is flowing through the wire or across the surface in general, but we'll consider them through wires and elements. And similarly, this voltage, also you know that the mathematical definition of voltage is the integral of the electric field. Okay. So basically, a voltage difference between 2 points represents the energy gained by a unit charge by going from the first point to the second point. Okay. So we'll deal with these things instead. Now, why are these things useful? Again, like I said, the point is that we'll have electrical elements which have at least 2 terminals, and this definition of voltage and current lets us deal with only the terminal characteristics. Okay. We won't have to worry about the spatial extent of the device or how it is arranged in space and so on. If you deal with charges and fields, you will have to do that. Okay. So it turns out that for our purposes, we can simply look at the voltage difference between the terminals and the current through the terminals and make some relationship between voltages and currents, and that completely characterizes the element. Okay. And using these terminal characteristics is much simpler than trying to find the distribution of charges and fields. Okay. So just like in gravity, a mass falls from higher potential to lower potential, a positive charge falls from higher potential to lower potential in an electric field. Okay, that's the definition. So if you have an electric field like this, Okay, you know that a positive charge will tend to move in that direction. So first of all, this means that 1 is at a higher potential than 2. Okay, and how much higher is basically characterized by the potential difference V1 minus V2. Okay, and the unit of potential difference, it is volts. Okay, so basically if 1 coulomb of charge moves over a potential difference of 1 volt, it gains 1 joule of energy. Okay, so the volt is nothing but 1 joule per coulomb. So now we could say that, let's say the point 1 is 1 volt above point 2. Okay, and we could equally well say that point 2 is 1 volt below point 1, which is exactly the same as saying point 2 is minus 1 volt above point 1. Okay, now this is kind of obvious. Now this is like saying the upper floor of a building is 10 meters above the ground floor. That's of course legitimate. We could also say that the ground floor is 10 meters below the upper floor, and we could also say that the ground floor is minus 10 meters above the upper floor. Okay, it's a weird way of saying it. In normal conversation we won't do it, but with voltages frequently you encounter both positive and negative potential differences, and you should be comfortable working with them. Okay, so saying that point A is 1 volt above point B is the same as saying point B is 1 volt below point A, or point B is minus 1 volt above point A. So the same thing can be said in many different ways, and you should become comfortable with this.